Hi, in a previous video I did some days ago, we looked at interpreting coefficients in a Cox proportional hazard model where the only explanatory variables were categorical. In this video, we're going to be looking at interpreting coefficients where we have multiple explanatory variables, meaning that we think there are more than one variables that affect survival time, and we put those variables in to the model. Specifically, we're going to be focusing on confounding variables. The example is taken from the book by Hosmer and Lemeshow, 1st edition, chapter 4, at the start of section 4.4. You don't need the book, but if you have it, you can read up on it. And the code, as always, is on the website. Okay, so the first thing is to look at the dataset. So I'm introducing you now to the dataset. Got the book in front of me. This is taken, data here is taken from a study whose purpose was to compare treatment programs of different planned durations designed to reduce drug abuse and to prevent high-risk HIV behavior. So yeah, it's a health example. And what are the variables then? Well, the variables we're going to be looking at, we're just going to be needing today, is IVHX, which stands for IV drug use history at admission. It is a categorical variable, and I'm just telling you that you can't tell by looking at this, but I'm telling you because I have the book in front of me. It's coded 1 for no history of IV drug use at admission of the program, and coded 2 and 3 if there were. Okay. 2 stands for there's previous history, 3 stands for recent history of use. And the other one we need is treat. So this is also categorical. It is coded 1 for long treatment and 0 otherwise. And we also need, actually we don't need treat at all, we need age. Right, age is continuous. Right, that is continuous. So if we look at the first guy, or first individual, let's say 39 years old at the entry of the program, coded 3 for IVHX, so that means recent history of IV drug use. Yeah, that's all we need. Censor, as before, so there's a censoring, possibility of censoring going on here. 1 equals return to drug use, 0 did not return to drug use, or we don't know yet. Following the book to make this as simple as possible is that we're going to recode the IVHX, because it's currently one of 3 groups, 1, 2 and 3. We're just going to code it to 1 if there's a history of IV drug use and 0 otherwise. Right, so we're going to recode this guy. So let's do that. So I've done all the hard work before. Okay. Right, so what this says is that from the variable from that data set called dat, I'm going to call any value that is less than 2, I'm going to recode it to 0. Okay. And then any value greater than 1, I'm going to code it 1, standing for there is drug use. Alright, so there you go. So that's now done. The next thing I want to do is, I'm now looking at page 132, where it tells us that we note that age is missing for 5 subjects, and the IVHX has 18 missing. Well, let's just confirm that. Let's confirm that. How do we confirm that? Let's do it for doing it for age, and the command we need is this exclamation mark complete dot cases. It's like not equal to not complete cases. Okay, I'm going to list them by row. So here you go. So we've got cases ID 1, 1, 0 and so on. And we've got 1, 2, 3, 4, 5. So as the book says, 5 missing for age, right? Doesn't mean missing for all of them, just so long as, so all the other ones have ages, but these 5 individuals, we don't know their age. They didn't complete the questionnaire properly, or we don't know anyway. Maybe they were shy or just didn't complete to reveal their age. And we can see that these 4 people also, we don't know about this variable here. Okay, so what's going to happen is that in this example is that we're going to omit these observations. So it's like deleting them list-wise. What we want to do then is to extract from this dataset only where we have complete cases for time, sensor, IVHX, and age. So that's this command here, complete case again, this time without the exclamation mark. Do that. And now we're ready to fit the model. Okay, by the way, when I'm showing you this notepad or the code, I don't expect you to be reading as I'm talking, though I know it can be a hindrance. You're trying to see what I'm doing. I'm just following the story here, but the code is pasted into R, and anyway, it's available on the website. So what we're going to do now is going to fit 2 models. Remember, the focus in this video is one on interpretation of the coefficients and also this thing about what they call confounding. So we're going to fit 2 models. One is that we're going to fit a Cox proportional hazards model to the IV, the history of IV drug use first. And the method I'm going to use following the book is the Breslow, although we know that is the Efron one is more exact, and even the exact one is more exact than this one. So and there is better than this. I've got an error. I got an error because I have not remember to load the package survival before you do this. Okay, now do it. All right, and now we look at it. IVHI exactly. Okay. Alright, so that's the coefficient we've got, and that's the exponential of, or e to the coefficient value. Let's just record those 2. I'm ignoring everything else for now, I'm just recording those 2 values. Let's do it in Excel. So here's something I prepared earlier. This is what we call the crude model, and we've just done drug, which is IVHX. Maybe it's better I just put that in comma so you know it's IV history of. Okay. Coefficient there is 0.321. Okay, and then what is the e exponential of that? Well, I could just record it or just be lazy and just take exponential of this, because that must be the answer. 1.38. Yes, 1.38. Okay. And let's go back to this. Right, so we're running 2 models. This is just having the explanatory variable drug. And next, and this is where the multiple explanatory variable comes in, this is the new bit, we're adding in drug and age. Alright, but before we do that, let's just recap on the interpretation. This is from last time. So recall that if we look at this coefficient, and the coefficient is equal to 0, theoretically equal to 0, that means there is no change in the risk for a person who has drug use compared to a person who has no prior history of drug use. No risk of the event, and the event here, thank God, is not death, it's time to return to drug use. Okay, the time variable here stands for time to return to drug use. That was what was recorded, measured in days. So quick recap again. Yep, if the coefficient that I'm pointing at there is not equal to 0.321, but say equal to 0, that means there's no change in the risk for a person who is on drugs versus someone who's not had previous history on drugs. If it's greater than 1, it means that the person who has a prior history of drugs increases the risk of return to drug use. And if it's less than 0, it's the reverse, so then it's a decrease in the return to drug use. But the coefficient of, let's go into the exponential now. If we don't want to we usually look at this exponential, the e of the, I prefer to say e of the coefficient. that tells us the hazard ratio, and if the hazard ratio is 1, it means that there is kind of no difference in the risk in the return to drug use for the two groups. So there's no difference in the whether or not you have a prior history of drug use. Doesn't kind of impact your risk of the return to drug use. If this number, exponent e of the coefficient, is greater than 1, that's the same as that saying it increases your risk if you take drugs, and if it's less than 1, decreases your risk if you take drugs. Alright, so usually we're looking at this guy, not this guy. Okay, now what we want to do now is, like, we can say that this model is probably too simplistic. There's probably other things, other explanatory variables that affect this survival time, and we're going to consider age here. Alright, so this is where the multiple bit comes in, because we've got not one now, we've got two explanatory variables. And we're going to be really interested in what happens to the coefficient on drugs when we do that. Okay. So same as before, just simply this time we're just going to add, same as before, just add age. And then we'll look at it. Right, here you go. Those two numbers that we need to record. So let's go to Excel again, and let's just put those numbers in, so you can trust that I'm going to type this in correctly. 439. Drug age minus 0.026 equal exponential. Right, just another way to get the hazard ratio. Take the e of the coefficient. There. So what we can see is that the coefficient of the drug here is still positive, and still positive, but it's increased. What does it mean in terms of the e of the coefficient? It means it's also increased. To recap the interpretation of this guy, 1.38, say, that's saying, like, the risk of someone returning to drug use, if they have a prior history of drug use, is about 38% higher than for a person who has no previous history of drug use. So what you can say here then, now it's gone up to 55%. Why has it done that? Well, the simple thing is this. This guy here, the first mole, did not take account of other possible explanatory variable that could also impact survival, impact the time to event here. In this case, age. Right, so age also impacts the survival time, and more importantly, it is also kind of related to drug, this variable. And so something like that, a variable like that, which does affect the time to the event, the thing we're interested in, and also is, I was going to say correlated, but yes, is kind of related to the thing that is related to the explanatory variables in the model. If you do not put that into the model, i.e. you omit it, and it is relevant, then what you get is a coefficient value here, an estimate, which is basically off. It's kind of off. It's too high or too low. Technically speaking, it's inconsistent. So here, as a result of not putting in something which is relevant like age, it's actually under predicted the impact of drug use on survival time. This variable then, age, which is relevant but was omitted, it's something we're not actually interested in the coefficients. We're interested in these coefficients because that's the aim of the program of the study, was to, I said right at the beginning, was to look at the impact of drug and treatment on the survival time, least that's what I think of what I said. So anyway, we're interested in this coefficient on IV HX, the drug use, not age. We're not really interested in age, but we want to like control for it. That's another way of saying it. Okay, so this guy here is then called a confounding variable. We're not interested in the coefficients, but if we don't include it, it's going to make our estimates for the things that we want, going to make them wrong. So what is the lesson here? It's, if you're only interested in the looking at the impact of one variable, one explanatory variable on the time to the event, but there are other variables, explanatory variables, that you're not exactly interested in, but they are also kind of impact the time to event, and they're also related to the thing in your model, then you've got to put them in even though you're not interested in them. And those guys, they're called confounding variables. How do you know if you got confounding variable? Well, one thing is to check that the thing that you put in here, like age, that is significant when you stick it in. Is it significant? Yes, p-value is low, so it's significantly different from 0. And also, not only that, is it kind of related to, remember there's two things that have to happen. The confounding variable is related to two things. It's related to the time to the event, and it's also related to at least one of the x's, the explanatory variables in your model. So how can we see then it is related to the thing in my model being IVHX, previous drug use? We can calculate the mean of the age across the two groups. If there's no relationship, then the mean age across those two groups should be the same, i.e. the mean age for those people with previous history of drug use and no previous history of drug use should be about the same. Here we see there's a difference. Okay, I don't know if it's a significant difference, but anyway, it gives us an idea. Well, we could test this formally, but the book doesn't go into that kind of detail, so let's not bother. That's not the kind of aim here. And then, so so we've seen two things then, that the age is a significant explanatory variable in the model, and also it's kind of related to the kind of the drug IVHX drug use, the explanatory variable in the model. Also, one final thing is that if the coefficients are not that much different, then we can let it go. But if there's a big difference, like here, then we must do something about it. In other words, we better take this model, not this model. Very subjective to say, what is a big difference. So you could actually calculate a percentage difference between these two guys to report it, if you like. So, just to say there's a difference of 0.55 minus 0.378, and give them a number or a difference between these two numbers. If you just report a number, that doesn't really mean anything to anyone, because we don't know what kind of scale you're measuring things on. So it's better to report percentage change. So percentage change, a recap on that percentage change. How do you do percentage change? Let's look at the coefficients, just like in the book. You take the and we're looking at the percentage increase, because you can see that coefficient's gone up from 0.321 to 0.4439. You take the new value, 0.439. You take off from that the old value, the one we started off with, 0.321. Then you divide that whole thing, give you a proportionate change by the whole value. Okay, and then to that you can add 1, because that's the factor increase. So going up from 0.32 to 0.4, about 44, represents a factor increase of 1.3676. In other words, about 37% increase. To check that's right, you take this figure, old figure. I'm telling you that the factor increase is that guy, and if we press equal, it should give us this guy, which it does. Okay, so we've got a 30% increase going from there to there. That's sizable, even if we think about being subjective. Alright, so pretty much that's it. So what's the lesson today? It is that we have to take account for confounding variables. And if you think about it, it means that where we think there are many kind of explanatory variables that impact survival time, we cannot just run many simple models just running single explanatory variables on the survival time. In other words, it wouldn't make sense just to do drug by itself, like we've done here, on time, and also do a separate one of age on time, and so on, building up a model that way. So there's a real need for multiple covariate models. As a final step here, we've called this crude model because that's the kind of, it's crude, it's just got one explanatory variable. This is the adjusted one. Now where we have kind of two explanatory variables, we can actually have a third possible model. What can I call it? Adjusted 3 or something? Doesn't really matter anyway. Okay, still adjusted. We can think that drug use and age, they can have like a interactive effect on survival time. That's the kind of interaction, that's the formal word. Layman's terms, a combination effect, so different values of qualitative. It's hard here because this age is continuous, drug is categorical. So what I'm saying with this guy here, this actually means age times. It's actually time, so you take that figure, then you times it by age for each row, for each individual, to get a value, and that's a new explanatory variable. And what this does, it's talking about combination effect. So it's like, you take drug A if you've got a symptom for something, you've got coming down flu or something, hay fever, and you're also kind of drunk or something from the night before, you take drug to relieve one symptom, take drug B to relieve another symptom. Those two drugs by themselves have a kind of a effect on your body, but if you take them two together, you can imagine that those two drugs could influence and kind of give you another effect. So that's what this is. So interaction effects are pretty interesting to look at when you're doing biostatistics. So is there such an effect here? Well, let's run and see, and I'm going to show you that there isn't. So what we do is we just do one explanatory variable times the other is the shorthand way to do it. If you wanted to do the full way to do it, you would, anyway, I'll show you in a moment. What we find here, is it the interaction significant? No, p-value is greater than 0.05, so there's no need to go into that. We'll go into that another time. At this stage, just finishing off, let's just show you that I could get it another way. I'm saying that this is the shorthand way to do it, just do two variables multiplied by each other, but if you wanted to type it out in full, you can see what we've got is IVHX plus age plus, and then IVHX, and then the R notation is this colon and age. Oh, sorry, typo. What is that? X. Okay. And then I'm lazy, so I just trace up through the commands. You see the output's the same. There you go. Alright, so that's the first look at multiple covariate models, and there's more to come.